Okay, so thank you, Danuta, for that introduction, and thank you to the organizers, Stellar and Eurolax, for this opportunity. I'd also like to acknowledge my co-presenter, Dilip Asthagiri, as well as our graduate students, Arjun, Jinlu, Ziliang, Xingling, and Yunke, Professor Hirasaki, Professor Chapman, and Mark Fleury. And we'd like to acknowledge our sponsors, Chevron, Rice University Consortium, American Chemical Society, and the computing centers at NERSC and TAC. So here is the outline. Start with the motivation. We'll then show you some measurements on viscous fluids, including the polydisperse polymers and bitumen. Then the fluids under nano-confinement, namely heptane saturated kerogen isolates. And then I'll give it over to Dilip to talk about the MD simulations of water and alkanes and the simulations of heptane confined in a polymer matrix. So there are many mysteries in NMR petrophysics. The two that we will focus on today are viscous fluids such as bitumen, which is basically a heavy crude oil, typically larger than 10,000 centipoise, does not follow the Bloomberg and Cressell-Pound model. Namely, the T1 log mean is proportional to frequency, which is an anomalous dispersion, and it's independent of viscosity and temperature. The T2 log mean is inversely proportional to viscosity to the square root, and that does not follow the Stokes-Einstein-Debye relation. The other mystery, fluids under nano-confinement in unconventional shale, they show this contrast. So namely, light hydrocarbons and kerogen have a large T1 to T2 ratio for the surface relaxation, whereas water in clays or water in kerogen has a much lower T1 T2 ratio. And that's great for fluid typing and saturation, but why is it? Why is it a case? So these questions pose a fundamental challenge, but also they need to be worked out for practical reasons in petrophysics. So we believe the answers lie in understanding the molecular motions. And to do this, we take NMR measurements and MD simulations of these various systems. The first one is these polydisperse polymers. And I'd like to say from the beginning, this is very different to the monodisperse polymers that have been reported in the literature. Namely, we don't expect these polydisperse polymers to show much entanglement, or if any. So why do we use polydisperse polymers? Well, it's a model for bitumen because bitumen is also highly polydispersed. Also, these polymers have very high viscosity, up to 300,000 centipoise, and they have no paramagnetics, which allows us to investigate hydrogen-hydrogen dipole-dipole relaxation. We also use these polymers to form a polymer matrix to confine heptane. And here's a picture. The green here is heptane molecules confined in a polymer matrix, which we can simulate and we can measure the same system. And this, of course, is a model for heptane saturated kerogen pellets, namely immature kerogen. So that's what we're doing. Another reason to do NMR measurements and MD simulations is this nice picture taken from Wildman and Kern for proteins, but the same principles apply. So NMR measurements span a large range of molecular correlation times, so does the MD simulations. And we can investigate the collective modes, flexibility, local modes, and all these molecular modes. And that's basically our goal, is to do this for viscous fluids and fluids under confinement, nano-confinement. Okay, so let's look at the viscous fluids, and you're, I'm sure, all very familiar with the Bloomberg and Cressell-Pound data. So they tested their theory using glycerol, which is a hydrogen bonding fluid, and it's a great property because as you decrease the temperature, the viscosity really increases up to the glass transition. And so here we have the T1 and T2 versus viscosity over temperature. And in the fast motion regime, where omega tau is much less than 1, both are inversely proportional to viscosity. In the slow motion regime, where omega tau is much greater than 1, T1 shows this upturn, whereas T2 keeps going down. So this basically works quite well. It proves their theory is basically correct. This is a simplified model, the Lorentzian, the T2, and of course we need a relation between the correlation time and something we can measure, which is viscosity, and this is the Stokes-Einstein-Debye relation, where R is the hydrodynamic radius of glycerol. And there have been improvements, of course, to explain why this doesn't follow exactly, such as models such as the Cole-Davidson model, which basically posits a underlying distribution in correlation times, in molecular correlation times. So now on to the crude oils and the bitumen. And so this is the T1 log mean from various sources, namely Yang and in the Hirosaki group at Rice, vinegar from Shell, La Toraca from Chevron, and caustic from Schlumberger. And so these, as you probably know, crude oils are very complex systems, highly polydispersed. They have saturates, aromatics, resins, and of course these asphaltenes. So here's some data put together from all these sources. T1 log mean versus viscosity over temperature. Again, in the fast motion regime, we see pretty good agreement with BPP, but you can clearly see that the data plateaus or becomes independent of viscosity at high viscosities in the slow motion regime, and it happens as a function of frequency shown here. The latest data is this 400 megahertz data in this collection. I should note the 2 megahertz were the Athabasca bitumen, the oil sands in Canada, have a very large amount of paramagnetics, elemental paramagnetics larger than 1,000 parts per million. And there's of course also the radicals. And so these crude oils do have a lot of paramagnetics. But now let's compare this to the polymers, which do not have any paramagnetics. Here is the polymer we're looking at. It's polyisobutene. It's a Brookfield viscosity standard. The highest one they have is about 9,000 grams per mole. Again, that's the average. It's highly polydispersed. The viscosity can get up to 300,000 centipoise. And what we see is, we see very good agreement between the polymer and the bitumen at 2 megahertz in blue, 20 megahertz in red, and 400 megahertz in pink here. But the thing to note is that we did EPR on these polymers, and we found no detectable signal. And the resolution of the EPR was 100 ppm. So there's less than 100 ppm paramagnetics and radicals. So this implies that T1 log mean is independent of the concentration in paramagnetics and radicals in these systems. Therefore, it cannot be, this relaxation mechanism at high viscosity cannot be due to paramagnetics. As you know, the Bloombergen model from 61 shows that the T1 rate should be proportional to the concentration. Well, it's certainly not here. The other thing we did was we did molecular dynamic simulations of T1 for the polymer. The largest one, shown here by these green diamonds, the largest had a molecular weight of 912 grams per mole. It's around 1,000 centipoise. And at 400 megahertz, we see very good agreement with the measurements of the polymer and of the bitumen. And so clearly this T1 plateau is, again, independent of paramagnetics. Therefore, hydrogen-hydrogen dipole-dipole dominates in both the bitumen and the polydisperse polymers. And we're not using any models to show this. We're just looking at the raw data. Another way to plot these crude oils and polymers is to normalize the y-axis by frequency, basically divide by F0 and multiply the x-axis by F0. What that does is it collapses the data pretty much onto some universal curve. And we can characterize this plateau here. These lines, by the way, were just a guide for the eye. They're the average of the data. It's around 3 milliseconds. So basically at 2.3 megahertz, T1 log mean is 3 milliseconds. At 20 megahertz, it's 30 milliseconds, etc. So that's the T1 log means. The next thing we did was we investigated this more using field cycling. Okay, and here we show the field cycling data in open symbols for the different polymers for low viscosity to high viscosity. So this is T1 against frequency. And we also compare with the static fields, and we see good agreement. And we can see that, okay, at low frequency, there's definitely some viscosity dependence, but as you get towards high frequency, they merge, and this is the 400 megahertz point. This is the MD simulations shown here in the slow motion regime. So for the molecular simulations, that corresponds to frequencies roughly larger than 100 megahertz, and the viscosity is larger than 100 centipoise. And we see that the MD shows that T1 is proportional to frequency. Now, again, we see good agreement. BPP is obviously a poor agreement. It's supposed to go as F0 squared, and it's supposed to have a viscosity dependence. Obviously, it does not. Now, to look into this further, we developed a new model, and it's a phenomenological model. So instead of the BPP factor here, it's supposed to be a 2. Well, we changed that to 1. So this is basically a data-driven model. And what that does is, in the slow motion regime, it basically tau drops out and T1 becomes proportional to the frequency, as observed here. And it turns out that when we do this, it's actually quite similar to the Cole-Davidson function. When you take the exponent of the Cole-Davidson function to very small values, it actually becomes independent of the exponent. And then you can recover this relation here. And what does this imply? Well, it implies that there is a large distribution in molecular correlation times, which we can access with the MD simulations that we show later. Now to T2, this is T2 log mean against viscosity over temperature from the same authors. And what's shown here, again, in the fast motion regime, T2 is roughly follows BPP, but you see in the slow motion regime, we have this anomalous exponent of -1/2, as shown here, and it's roughly above 100 centipoise. And there are 2 theories for that. One is from Jean-Pierre Corbes to explain this 1/2 exponent, and the other, slightly more recent, is Ravi-Kosik's theory. And so, yeah, more investigations required to see which is applicable. We saw the same thing for the polymers, okay? This is now a collection of data, data from Shikov et al. And Arns, and it's a deoxygenated alkanes. It follows the BPP very well, but our polymer data, again, has this anomalous exponent, and the MD simulations agree pretty well, shown here. And again, independent of paramagnetics. Let's look into a little bit more detail about the fit. And here we show the most viscous polymer. We show T1 and T2. T2 is in black, and T1 rho in red. And what we find is the model agrees pretty well. Okay, this is for 100,000. This is for the lower viscosity, lower yet, and then the lightest. Okay, so the model fits quite well. And this is the model both in the slow motion regime and the fast motion regime. So really, thanks to the field cycling data, we're able to extend the analysis of our model. Okay, so that concludes the measurements of the viscous fluids. Now let's look at the measurements of the heptane saturated kerogen isolates. So many of you may not be familiar with this kerogen. And we start with a shale rock. In this case, it's a Kimmeridge oil shale, which it's a UK outcrop on the coast of Dorset. It's an immature type 2. And it has a very large total organic carbon, which makes it a great thing to study. So it's 10 weight percent, or equivalent to 18 volume percent of the rock is organic material. So we isolate the rock using hydrochloric and hydrofluoric acid. And we're able to increase the percent of organic matter to 84 volume percent. So basically, this is mostly organic material. We then take this kerogen powder and we pelletize them at high stress, an 8mm press. It's about 1 gram of material. And then we expose these pellets to heptane. We saturate them with heptane. And what we find is these pellets swell by 50 volume percent. Okay, that's a lot. And that's a direct consequence of this dissolved heptane. So let's see what this looks like in this illustration. So we have these kerogen grains. The kerogen is in black. The scale here from BET gas absorption is 100 nanometers. And the red is heptane. So we have two environments. We have the intergranular heptane in these 100 nanometer pores. And then we have the dissolved heptane, which cause the grains to swell. Now a bit about these dissolved hydrocarbons. So in the industry, it's been shown that in gas shale, in shale gas, there can be as much as 20 weight percent of gas in kerogen, dissolved in kerogen. The remaining 80 weight percent is adsorbed in free gas. But this 20% dissolved gas is typically neglected when they count the total gas in place. And it could be recoverable by pressure depletion. A bit more about these, this dissolved gas. Well, these are density functional theory computations of hydrocarbons in kerogen done by Liu and Chapman. And what they do is they first calibrate their density functional theory to swelling data. So here is swelling, the data, the bars for pentane up to benzene, and at different maturities. So this is in increasing maturity, and you can see the amount of swelling for each solvent. And then the lines here are the density functional theory. So once that's calibrated, once they calibrate that, they can then look at the difference in solubility of different components in kerogen. And what stands out is CO2 is much more soluble in kerogen than methane. And so perhaps this dissolved methane can be extracted with CO2 enhanced oil recovery. Okay, let's look at what the T1, T2 map of heptane saturated kerogen looks like. This is from Chen et al. So what we did here, we plot a T1 versus T2. Okay, projections shown here, the one-to-one line. We see two peaks, two distinct peaks. We put our cutoff, the T2 cutoff, around 1.7 milliseconds. And this peak here is the intergranular. The peak to the left is the dissolved, okay? We have these porosities defined here. Now phi mu, the microporosity, if you like, is the actual porosity of the grain itself. And it's computed in this way. Now, when we look at these T1, T2 maps, the first thing I always try and do is say, oh, what's the T1, T2 ratio of this peak? And I have to kind of look at diagonally. So what we like to do is rotate this and actually plot T1, T2 ratio versus T2. So this is the same data, but plotted by T1, T2 ratio versus T2. So again, the T2 distributions are obviously the same. And we can really tell what the ratios are at each T2. And what this does as well is, as you know, from surface relaxation theory, the fast diffusion limit, we have 1 over the T1 is given by surface to volume ratio of the pore, and this parameter, rho, which is surface relaxivity, and it's basically proportional to 1 over pore size. But when you divide T1 by T2, the geometry or the pore size should drop out, and you're left with a function of omega times the correlation time. So you can think of this axis as the correlation time. So the dissolved heptane has a much longer correlation time than the intergranular, which makes sense because it's more confined. So let's go back to our picture of these grains. And what we did next is we partially evaporated the sample. Okay, we open the cap, we could have a controlled evaporation of heptane. And what we find is what's left is just the dissolved fluid, okay? And that basically validates our thought about which fluid is where. Let's see. Some analytics. So the intergranular porosity is around 36 pu, and that's sounds familiar, and that's actually the same as a random packed monodispersed bead porosity. Low T1, T2 ratio. The dissolved heptane has a microporosity of 13 pu and a very large T1, T2 ratio. And so that's great. We have a large contrast in T1, T2 ratio to be able to distinguish these. We also did some version, but saturated with water instead of heptane. And basically, we see a lot less dissolved water in the kerogen, again, as expected. And finally, on these, we also compared with the water and clays. And so we have, again, our heptane dissolved in kerogen against the clays here, shown here. And we really see a good contrast. So that's a great thing for fluid typing. You know, this can be done in the lab or downhole on a logging tool. And it can basically get saturation from NMR. So basically hydrocarbon saturation. But again, what's the mechanism? What's the real mechanism behind this, okay? And this is where simulations will help us. Before that, we also need to figure out, again, what the relaxation mechanism is. And to do that, we investigated water-saturated kerogen versus partially deuterated water-saturated kerogen. And this is a similar technique that was used by Straley in water-saturated carbonates to show that hydrogen-hydrogen dipole-dipole relaxation exists in carbonates. And what you can think of it, let's look at this illustration here. So we have the hydrogens on the wall of the kerogen. We have the water here on the surface. And that's shown here by the blue. This is the T2 distribution. But what we did, we put 90% D2O, 10% H2O, 10% just to have enough signal. And what that does is it basically reduces dramatically the intramolecular. So between H and D is very small, the interaction, because of course deuterium is a much lower gyromagnetic ratio. It also reduces the hydrogen to the other molecule, the other water molecules, or the intermolecular. And what that does is it shifts the T2, okay? So it reduces the T2 relaxation. And the only way to explain that is through HH relaxation. If it was paramagnetism, there would be no shift here. So deuterating in this way really shows you what the underlying relaxation mechanism is. And we can basically get some idea. This hydrogen intra to inter between two water molecules is around 50 milliseconds. And the remaining relaxation, well, of course, we can't deuterate the kerogen, so we can't tell for sure, but it's very reasonable to assume that this is from the kerogen wall, which also has many hydrogens. Another evidence for hydrogen-hydrogen dipole relaxation is from Washburn and Chen, where they took heptane-saturated organic shale, and they looked at the T2 versus T2 exchange map, and they found these cross peaks, which they say is due to hydrogen-hydrogen intermolecular interactions due to magnetization transfer between heptane and kerogen. So that really sets the story to go down now to the molecular dynamics simulations of these hydrogen-hydrogen dipole-dipole interactions. Dilip?
Yep. Thank you, Philip. So as Philip mentioned in the first parts of the talk, one of the puzzles that we want to understand is the basis for the contrast that we are seeing. And this motivated us to do molecular simulations. So next slide, please. So we are going to be doing classical molecular dynamics simulations. So essentially we have the Hamiltonian given by a bond term, an angle term, a dihedral, and a non-bonded term. And we derive the forces from this Hamiltonian, and we are going to be using the charm general force field. I will mention one result where we have done a non-paraditive model based on amoeba that was for water. We take particular care in equilibrating the system for a long time under constant number of particles, volume, and temperature. These are typically for at least 2 nanoseconds long, where the equations of motion are propagated every 1 femtosecond. And just to emphasize, during this phase of the equilibration, there is a numerical thermostat that is controlling the temperature. After that point, we remove the thermostat and we do a production run at constant number of particles, volume, and energy. So these are these simulations run for at least about 2 nanoseconds. So this is just pure Newtonian dynamics, and we record the configurations every 0.1 picosecond. We go up to a lag of about 200 picoseconds for the bulk alkanes, but for the confined fluids, we have gone to a much larger lag time. Next slide, please. So from the record of the simulations, we can extract out the autocorrelation function. So on the left panel, what you have is we are showing you a simulation, a snapshot of heptane in bulk heptane. The spheres there are meant to represent protons. So you can have many different pairs of protons. These are just one example that we are taking. And so we can, knowing the position of the 2 protons as a function of time, we know the behavior of the mutual vector and the angle that vector makes relative to a fixed frame. And a similar principle applies when we look at the intermolecular correlation. So from this record of angles and distances, we can construct the autocorrelation function as described in the next slide. Next slide, yeah. So as I just mentioned, we have the intramolecular and the intermolecular, and that is our equation on top for our autocorrelation function. So theta ij is the angle that we have the record of as a function of time, and rij is the vector between the 2 protons, and we also have a record of that. And using this information, we can pretty much extract all the properties that are of interest. So we can get the correlation time, and we can get the second moment. And from the second moment, we can directly get the T1, T2 values without recourse to any adjustable parameters. Okay, so we did this initially for bulk fluids. So these are N-alkanes going from C5 to C17, and for water. And again, just to emphasize, these are pair additive force fields. For water, we have used TIP4P 2005. But we have done the same calculations for water with amoeba, and we get similar results. What is important to observe here is we get an excellent agreement between simulation, which is on the y-axis, and measurements. Again, without recourse to any adjustable parameters. So this work was published in 2017. Since then, we have made further studies. We then looked at the behavior. One of the interesting observations that we made was the the change in the relative proportion of intramolecular and intermolecular as we go along in chain length. So what we find is as we go higher in chain length, as we go from C5 to C17, the intramolecular dominates for the N-alkanes. But for the cyclic compounds, benzene and cyclohexane, it is the intermolecular interaction dominates. And so these are features, these are insights that are very difficult to obtain from direct measurements, but it's easy to extract it from computer simulations. Next slide, please. So once we have established the validity of our model relative to data, and I'm not showing you the diffusion data for bulk, and again, that agreement is excellent. What we went ahead and looked at is how do these autocorrelation behaves. So the total autocorrelation, as is clearly shown in this normalized plot. So we normalize it by the value at time t lag t equal to 0, and the x-axis is normalized relative to the correlation time. What you find is that the total autocorrelation is clearly not mono-exponential. So it clearly does not conform to the BPP model. In fact, in a recent paper that we have just submitted, we have looked at pairwise interactions between two protons. And even that does not conform to the mono-exponential that is predicted by BPP. So we need to understand why this kind of a stretched exponential or non-dependence is arising. And so we have looked at, again, intermolecular correlation. And this is essentially the Torrey-Hong-Fried approach. Qualitatively, the behavior of the data in this normalized plot is consistent with this model. But quantitatively, there is still considerable disagreement. And you see that it is a fairly stretched exponential behavior. Okay. So now, having developed these ideas for the bulk alkanes, we said we'll take a look at heptane and polymer matrices. And this is, in the next slide, we'll show the system. So this is work done by a graduate student, Arjun Parambattu. This paper was published recently. So as Philip mentioned in his first part of the talk, what we are doing is we are considering mixtures of alkanes, heptane here, which is green in this pictograph, in this pictorial, and the polymer matrix, which is shown in gray. And so we can change the relative proportion of the polymer and the heptane and make it consistent with the experiments that are being conducted in the laboratory. And we can examine a range of confinement. So greater than 50%, we call it a pore fluid. And as you can see, in greater than 50%, it is pretty much the heptanes are talking to each other. But as we increase the confinement, the heptane is talking more, and I'm using the word talking to just give you a physical feel for what is happening. The heptanes are talking more to the polymer matrix, which is our model, eventually our model for the kerogen. So having developed these, having built these systems, Arjun did heroic calculations, which were fairly extensive calculations. And we first decided to look at the behavior of the diffusion coefficient of heptane in the polymer matrix. And this, by the way, this plot has maybe touches upon some of the initial points that Professor Crook started off with. What we see here is on this normalized scale of diffusion versus volume fraction, what you see is a very strong power law behavior. The square symbols are the measurements, and the dots are the MD simulation data. There is a reasonable agreement between the measurements and simulation. One thing I do want to emphasize is at the lowest volume fraction, simulations do become very challenging. We have to do very extensive calculations, and Arjun has actually done multiple simulations, and we are showing you one of the cases where the agreement was the worst at the lowest volume fraction. The important point here is that the diffusion behavior follows a power law behavior, and this is essentially the Archie model. But the Archie cementation exponent is not 2 as you expect for a capillary pore bundle. Instead, you have an exponent that is 3.5. So it's hinting to us of a complex pore structure. Okay, so we see restricted diffusion in a complex pore structure. Okay, and again, I think there are things to understand about the dimensionality of this system. So next slide, please. So we then went ahead and looked at what is the impact of this confinement on the autocorrelation function. So this is just showing the raw unscaled autocorrelation function. So the blue line is the bulk intermolecular autocorrelation, and as we increase the confinement, you see a dramatic shift in the autocorrelation in the time scales. Okay, and this is clearly a fairly stretched exponential. And so one of the standard ways to deal with this fairly stretched exponential is to look at the underlying modes. And we use this inverse Laplace transform approach to discover the underlying mode. So on this plot here, on the right-hand side, we are showing the Laplace transform. So you have the probability, what we are trying to discover is the probability density distribution, which is shown in this red, the symbols are colored red in this equation, of the underlying correlation time. And I wanted to remind you that this is an issue that Philip hinted at when he was talking about the Cole-Davidson type analysis. And so on the y-axis in the plot is the probability density distribution versus the correlation time on the x-axis. And you can clearly see that as you increase, as you change confinement, there are different molecular modes that appear. In this plot, there are about 5 molecular modes that we discover. And if you apply the BPP filter to this, you find a very interesting point. So this BPP filter is essentially saying, it's essentially telling us the region of sensitivity. So for so this function here in this equation, the argument of this weighted that is being weighted by the probability function, that is essentially coming from the BPP idea. What you can say physically from this data is, for the inferred T1, timescales that are, say, 10 power minus 2 picoseconds, modes that are appearing at the timescales of 10 power minus 2 or 10 power minus 1, or modes that are appearing at 10 power 4 and beyond, do not contribute to the T1 that we are actually seeing at 400 at this frequency of 400 megahertz. Okay. So we did the same thing for the viscous polymer. Again, you discover these different peaks. This analysis was done at 400 megahertz. And this is for, again, just to remind you, for the polymer. And what you see again is you see the development of these modes in this system as you change the viscosity, going from, say, 1 centipoise to 1000 centipoise. Okay. So these are again all hinting at we are trying to go towards finding an explanation for the contrast issue that Philip mentioned in the first part of the talk. So now we look at the distribution of T1, the behavior of T1 versus confinement. What you see is T1 rather dramatically decreases with confinement. And this is exactly where the contrast is emerging, okay, as we will show in the subsequent slides. And just to emphasize to you, the T1 changes has a fairly broad range from 7,000 to 20 milliseconds. And the analysis and this analysis was done at 2.3 megahertz. And the simulations were also done at, simulation was analyzed at 2.3 megahertz. One point I wish I should have reminded earlier on, one of the advantages of the simulation is you just do the simulation once, okay? And once you do the simulation, you can change the frequency. It's a fairly easy matter to just change the frequency in the analysis. So that is one additional advantage of combining experiments with simulation. So the underlying configurations are the same. So now we can look at the distribution, the parity or the cross plot between simulation values of T1 and T2 and the measurement values. There is some deviation in the middle, and we have some ideas why that is happening. But overall, there is an excellent agreement between the simulations and measurements. And again, just to emphasize to you, the actual measurements were done in a fairly viscous polymer, and the simulations were not done with such high viscosities. But this is something we are aiming to do in future work. Okay. So now going ahead and looking at the behavior of, so once we have the T1, T2 in this mixture, what we can do, and we already have shown you how to get the bulk, knowing the rate of relaxation in the complex versus the rate of relaxation in the bulk, it's a simple matter to get the rate that is due to the surface. This again relates to the last part of the talk that Philip mentioned. And what you can see in this plot is the T1 behavior shows this changes with confinement. And importantly, what you discover is this rather remarkable behavior of T1 depending directly on F0, which was essentially the point that Philip started this entire lecture with. So for this confined heptane in the system, what you find is instead of the proportionality being 3 milliseconds, we get a value of about 7 milliseconds. But the basic idea of T1's, the surface components being proportional to F0 is recovered. And that's an important finding. And just to emphasize to you, this is again all done in this analysis of computer simulation data. There is no paramagnetism in any of these, in any of this analysis. So having seen all this, we can go ahead and look at how the contrast emerges. So what we see is as I go from the pore fluid to the dissolved fluid, and on this axis, we are going from right to left. What you see is as we increase confinement, you start seeing the emergence of the ratio, the contrast that Philip mentioned in the first few slides of his lecture. Okay, and again, once again, we were very happy to see that. And by the way, just to emphasize that the simulation data has been analyzed at multiple frequencies, from 2.3 megahertz to 400 megahertz. And we can now look at the comparison with respect to experiments. And while the quantitative agreement may not be exact, the qualitative agreement is excellent, given all of the issues that I mentioned with respect to the polymer viscosity is not being exactly right. And again, all of this is emerging just from proton-proton dipole-dipole relaxation without recourse to any without invoking any paramagnetism. So at this stage, I will turn over the stage to Philip, and he will wrap up with the conclusions.
Thank you, Dilip. So, yeah, to conclude, I hope we've shown you that the synergy of NMR measurements and MD simulations greatly enhances NMR petrophysics. And we're also looking at other avenues, such as MRI contrast agents. We found that the anomalous T1 dispersion and the T2 dependence on viscosity are the same for polymers and bitumen, and therefore due to hydrogen-hydrogen dipole-dipole relaxation, not paramagnetism. This T1, T2 contrast, again, is a very powerful tool in NMR petrophysics for characterizing unconventional shale. We found the same behavior for fluids under nano-confinement as we did for viscous fluids, namely that the T1 is proportional to frequency, a large ratio, and this indicates some kind of universal behavior. And that universal behavior we're hoping to capture using molecular motions, basically characterizing the molecular modes of the underlying distribution in molecular correlation times, where the objective is to achieve a library of molecular modes for various fluids, viscous fluids, various fluids under confinement, and to be able to predict basically things that we cannot measure in the lab. Okay, so that concludes the presentation. Since this is recorded, we'll just show you some of the references that were referred to during the talk, and you can look through these on the recording if you're interested. And I think that's the last one. And so, yeah, that concludes our presentation. I hope you enjoyed it, and we'll take any questions. Thank you.
Thank you again for this opportunity.